Hi everyone! In this video, we're going to learn about sets and subsets. We're going to define what we mean by set, subsets, empty set, and power set. And then we're going to represent set using the rule method or the roster method. And finally, we are going to discuss how to determine set equality. If you're ready, halina't matuto. Let's start with the definition. Naively, we think of a set as any collection of definite, distinguishable objects of our intuition or of our intellect to be conceived as a whole. The objects are called the elements or members of the set. So, any collection of objects which we can identify to form a whole can be considered as a set. Some examples, number 1, the set containing the numbers 2, 3, 5, and 7. So this set, the elements are definite, the numbers 2, 3, 5, and 7. The set of vowels in the English alphabet. So we know that there are 5 vowels in the English alphabet, namely A, E, I, O, U. So we were able to determine which are the elements of this set. Number 3, the set containing the provinces Aurora, Bataan, Bulacan, Nueva Ecija, Pampanga, Tarlac, and Zambales. So the elements of the set are properly identified. They are the mentioned provinces. Number 4, the set containing all the students of Bulacan State University. So in this example, the set is properly defined since it contains all the students of the said university. Number 5, the set of counting numbers. So it's identified that this set contained numbers 1, 2, 3, and so on. Number 6, the set of all people living on earth. So again, it's properly identified. Every people living on earth belongs to this set. Number 7, the stars in the universe. So, very important thing to notice that for you to consider a set, you must be able to properly identify the objects that belongs to this set. Some common notation, usually we use uppercase letters to denote the name of the set. For example, we use capital letter A, capital letter B, C, X, Y, C, and so on. So those are the usual naming conventions used to denote a set. On the other hand, we use lowercase letters to denote elements of a set. For instance, lowercase letter A, B, C, or X, Y, Z. Now, if we want to say that a particular object X is an element of A, usually we use the notation the E-like symbol. So we write X, the E-like symbol A, to mean X is an element of A. Now in mathematics, usually if we want to denote something is not, we usually use the slash in the symbol. So that means to write X is not an element of A, we write X, the element symbol with a slash, A. Now, if A contains more than one element, say x1, x2, x3, and so on, we write it shorthand as follow. So, we write x1, x2, and so on using the ellipse symbol, xn, an element of A, to mean that all of these elements or objects x1, x2 up to xn are actually element of A. We're already familiar with the set of natural numbers, integers, rational numbers, irrational, real, and complex number. So to denote this set, we will use the following symbol. For the set of natural number, we usually use capital letter N, but to make a distinction, we will use the blackboard letter N. The set of integers usually is written using the letter Z for the word Zahlen, which is the German word for integers. So we will use the capital blackboard letter Z. So that's like a Z, but we are using the blackboard version. The set of rational numbers, or also known as the quotient of two integers, where the denominator is not zero, is usually denoted by the capital letter Q, but we're using the blackboard version. On the other hand, the set of irrational numbers is denoted by Q prime. In abstract algebra, prime usually means complement. So that means the set of irrational number is actually the complement of the set of rational number. Of course, with respect to the set of real numbers, which we denote usually by the capital letter R. So the set of rational numbers is denoted by the blackboard letter R. Finally, the set of complex numbers is denoted by the complex or the blackboard letter C. Now, to define a set, we usually have two methods, either the roster method or the rule method. Roster method is simply listing of the elements of the set. So, when we write a set, we usually use the set builder notation or the open-close braces. So, we simply write the elements 2, 3, 5, and 7 inside the set builder notation. So, we write an open brace, then 2, 3, 5, 7, close. That means every element is identified and separated by the comma. Next example, the set of vowels in the English alphabet. So we know that the set of vowels in the English alphabet are A, E, I, O, and U. So we simply write that inside our set builder notation, A, E, I, O, U. Now, roster method is good if we identify each object, and of course if the list is small. But when the list started to become big, of course it is inconvenient to use the roster method. For that, we usually use the rule method. Now, the rule method specify a property that describe exactly what objects are members of the set. So if A is a set and P of X denote a statement which is meaningful to an object X in A, then we write the set of all element X in A such that P of X holds as follow. So in set builder notation, we write an arbitrary element X to be in A such that the condition P of X holds. So this will contain all object X in A that satisfy property P. So instead of listing the elements of the set, what we do is we describe. We give a well-defined description of the elements in the set. Some examples, the set of even integers. Now, the set of even integers are as follow. We have the numbers 2, 4, 6, 8, and so on. But of course, it also contains the number 0, and it also contains the negative even integers. So it also have negative 2, negative 4, and so on. So those are the elements of the set. So how do we write them in set builder notation? So all you need to do is to enclose in the parenthesis a description for the set. So for instance, we can use the set builder notation. X is an integer, so X is in Z such that X is even. Of course, mathematically speaking, we can have a formula for the even integers. Even integers actually can be written as follow. 2 is 2 times 1. 4 is actually 2 times 2. 6 is 2 times 3, and so on. So that means every integer can be expressed as 2 times an integer x, where, or let's use n instead, where n is an integer. And that's also true for 0. 0 is 2 times 0. Negative 2 is 2 times negative 1. Negative 4 is 2 times negative 2, and so on. So, mathematically, we can also write this using the formula 2 times n, where n is any integer. So, these two represent the same set. Similarly, we can do that for the set of odd counting numbers. So, what are the set of odd counting numbers? So, this comprise of the numbers 1, 3, 5, 7, and so on. Now, because we specify this to be counting numbers, so we don't have negative. We do not include the negative odd numbers. So, we only include the positive odd numbers. So, those are the 1, 3, 5, and so on. So, again, we can simply write inside the set builder notation a description for the elements odd counting number. So, x is a natural number such that x is odd. But of course, we can also use the formula for the odd counting numbers. Since 1 can be written as 2 times 0 plus 1, and 3 can be written as 2 times 1 plus 1, 5 can be written as 2 times 2 plus 1, and so on. So that means we can represent an odd number by the formula 2 times a natural number plus 1. But this representation, take note, does not include the number 1 if we are going to restrict n to be just the set of natural number. Because the set of natural numbers starts at 1. So, how do we include the number 1? So, we must include the number 0 in our representation. Or, we can use another formula. We can also use the formula 2n minus 1. Now, if we use this formula, then we can restrict n to be just the set of natural numbers, since 2 times 1 minus 1 is equal to 1. So that already, this formula will already include number 1 in our set. So we can use that formula. X can be represented by 2n minus 1, where n is any natural number. How do we write the set of rational numbers in set builder notation? So simply we can write it as x is a real number such that x is rational. But of course, a more elegant way to write this is to identify the formula for the elements of the rational numbers. So we can also use the set containing all numbers of the form P over Q such that P and Q are both integers, but of course we don't want the denominator to be 0, so we exclude Q equals 0 and say Q is not 0. Similarly, the set of complex number can be written as x plus iy such that x and y are real numbers, and we need to specify what I is. So I squared equals negative 1. Let's have some more example. The set of all square integers. So what does it mean to be a square integer? So a square integer is an integer which is formed by squaring an integer. So for example, 1 is a square since 1 is equal to 1 squared. 4 is another square since this is equal to 2 square. The next square is 9, which is 3 squared. So this is simply an integer times itself. So that are square integers. But we have a restriction that it's less than or equal to 100. So all you need to do is to get the squares up to 100. So that means all you need to do is to get 1 square, 2 square, and so on up to 10 square, which is 100. So we can write that using the formula n squared for all n that are integer, but between, of course, we want n squared to be less than or equal to 100. So we want n to be between 1 up to 10. The set of points in the Cartesian plane lying on the line y equals 2x plus 3. If we imagine, so there is a line in the Cartesian plane with formula y equals 2x plus 3. So when x is 0, y is 3. And when x is 1, y is 5. So this line here. So what we want are the points lying in this line. So any point here. So of course, a point in the plane is represented by the ordered pair xy. So our set is denoted by the ordered pair xy. So usually we denote a Cartesian plane by the symbol r squared. This is the Cartesian plane. And then we express the formula such that x and y follow the formula y equals 2x plus 3. The set of points in the Cartesian plane lying in the unit circle. So the unit circle can be illustrated by a circle whose center is the origin and whose radius is 1. So we all know that the formula of the circle is given by x minus the center squared plus y minus the k center equals r squared. So if it's the unit circle, then the center is 0, 0. So we have x squared plus y squared equals, the radius is 1 squared. So that's 1. So the set can be represented as follow. The set containing all points x, y in the Cartesian plane such that it follows the equation x squared plus y squared equals 1. So those are all the points in the circle x squared plus y squared equals 1. So now let's define what we mean by subset. So if we have two sets A and B, we say that A is a subset of B if and only if every element of A is an element of B. So everything that is in A is in B. So we write that using the symbol C with dash below. So it's like the handle of a cup. So if you can imagine a mug, so we have a symbol like C and then a half equal sign. So we say that A is a subset of B using this symbol. By definition, we write that as follow. For every object X, if X is in A, then X must be in B. So every element of A must be an element of B. Now, this equal sign here, this half equal sign here means it's possible that A could be exactly B. Still, the definition holds since every element of A is still in B if A and B are the same set. But if we are sure that A is not the same as B, then we can put a slash symbol in the equal sign, or we can simply use this symbol instead. So A is a what we call proper subset of B. So when we say proper subset of B, A is a subset of B, and we know that A is not the same as B. So there must be an extra element in B that is not in A. So there exists an X in B such that this X is not in A. So meaning, not all of the elements in B are in A. Now, if A contains some element that is not in B, then we say that A is not a subset of B. And we write that by putting a slash again in mathematics. When we say something is not, then we put a slash on the symbol. So, the symbol subset with a slash means A is not a subset of B. So, meaning, there is an element X in A such that this X is not in B. So, not everything in A is in B means X is not a subset of B. Several example, simple example, N is a subset of C. So the set of natural number is contained in the set of integers. Similarly, all integers are rational. So the set of integers is contained in the set of rational number. Now, all rational numbers are real numbers. So, Q is a subset of R. And R, since all real numbers is a complex number, then R is a subset of C. Or, more simpler example, the numbers 2, 3, 5, and 7 as a set containing one of those elements. In particular, 3, the set containing 3 is a subset of the set 2, 3, 5, 7. So, any set containing any of the elements of this set, for example, 2 and 3, this set is contained in the set 2, 3, 5, 7. Now, the set containing 1/2, since 1 in particular is not an element of this set containing 2, 3, 5, 7, then this set on the left is not a subset of the set 2, 3, 5, 7. So now, let's look at some properties of subset. For every set A is a subset of itself. Now, let's look at why that is true. Of course, it's very obvious to see why A is a subset of itself. But of course, we need to state it mathematically. So let A be a set. Now, for any object X, we know that X is in A will imply that X is in A. So that's a very simple statement. Since X is in A, then X is in A. But mathematically speaking, this follows the definition of subset. Any X in the first set is contained in the second set. So therefore, we can conclude that the first set A is a subset of the second set A. So that's how we prove the first property. How about the second property? If there are three sets A, B, and C such that A is a subset of B and B is a subset of C, then A is a subset of B. That's what we actually call the transitivity property of subset. We can write this simply as A is a subset of B in a continued inequality of set, and then or containment rather of set, and then B is a subset of C. So what the property is saying is that this can also be written simply as A subset of C. To show that, so let A, B, and C be sets such that we have the given A is a subset of B and B is a subset of C. By using the definition, A is a subset of B means for any object X, X is an element of A will imply that X is an element of B. On the other hand, the second given, B is a subset of C, means for any object X, if X is in B, then X is in C. These two are just the definition of subset. Now we have an if-then statement. In logic, we can look at it as P implies Q and Q implies R. So in logic, if you have two implications, P then Q and Q then R, then using hypothetical syllogism, we can just say that for every X, if X is an element of A, that's P, then we can simply conclude R, X is an element of C. But we know that this statement, mathematically speaking, means that the first set A is a subset of the second set C, which is what we want to prove. And so we are done. So here it's very important to recognize that we are using logic to prove properties of set. The hypothetical syllogism P implies Q and Q implies R gives us the required conclusion that P implies R. Now let's define what we mean by an empty set. There is one and only one set which contains no element. We call this the empty set or the null set. So we usually denote the empty set by a circle to denote the set and then a slash to denote that this set contains no element. Or in set builder notation, that's open and close brace. So again, we define this mathematically to mean that for every X, X is not in the empty set. So this set contains no object. This is a very useful definition of empty set in terms of proving, which we will later use. It contains all object X such that X is not equal to X. So that means you have a contradictory property. Later, we will often use this when we want to say that some set is empty. All we need to do is to find or assume that an element X is actually in this set, and then find a contradiction, which would mean that this particular X to start with cannot be in that set. So that set must be empty. So again, remember that property of the empty set, which will be helpful later when we want to prove that a set is empty. On the other hand, a set which is not empty is called a non-empty set. Let's look at some properties of the empty set. So for any set A, the empty set is always a subset of A. So this is really easy to grasp. How come something that contains nothing is a subset of A? So to form the subsets of A, usually it contains elements of the set. So if we remove all the elements of A, you're just left with the empty set. Now, on the other hand, if a set B is such that B is a subset of A for any set A, then B is empty. So this means that the empty set is indeed unique. There is only one set which contains no element, and that's the empty set. So let's prove the first one. We want to show that for any set A is a subset. Rather, empty set is a subset. So what we want to show, let me write that. So we want to show, usually I'll just abbreviate, we want to show by WTS. So we want to show that for every X belongs to the first set should imply that X belongs to the second set. So that's the definition of a subset. Now, the first statement, X is an empty set, we know to be always false. Right? Because X contains no element. By definition, if X is an object, then X is not. It is not in the set of empty. So therefore, if we say that X is an empty set, then that statement is false. So we have an implication with a false hypothesis or a false premise. So in logic, that means whatever the second condition is, then the whole statement is always a true implication. Again, remember the truth value of an if-then implication. So if you have if-then, the statement will always be true whenever the premise is false. Actually, we call that a vacuously true statement. So therefore, empty set is a subset of A. That's vacuously true. Vacuously true meaning because of the premise being false, no matter what the conclusion is, it will always be true. That's why it's vacuously true. Now, let's show the uniqueness of the empty set. So, we're given with a set B such that for any set A, B is a subset of that set A. For any set. In particular, because A is any set, we can conclude that B is a subset of the empty set. Again, because this say any set. So we're just getting a particular set. So this is a particular case. But since this is empty, it contains no other subset but the empty set. The empty set contains nothing. So its only subset is the empty set itself. So therefore, B is the empty set. Empty set is the only subset of the empty set. Therefore, B must be the empty set itself. Okay? Now, another interesting set that we want to discuss is the power set. For any given set A, the power set of A is defined as the collection of all subsets of A. So, all you need to do is to get the subsets of A. So, usually, we denote the power set using the script symbol P. So, the power set of A is the set containing all set U such that U is a subset of A. So, you get a subset of A, then that becomes an element of the power set. So, meaning U is an element of the power set of A if and only if that U is a subset of A. So, any subset of A. Well, from the previous discussion, we already have two automatic subset of A. We already know that the empty set is always a subset of a set, and A is a subset of itself. So that means that these two are always an element of the power set of A. Now, how do we get, in general, all the elements of the power set? For instance, let's say we have the set containing two elements A and B. So again, you just have to identify the subsets of A. So one simple idea or one simple technique to do that is you get an element of the set and then you form the set containing that element. So the singleton set containing A and the singleton set containing B are subsets of this set here. Let's call that A. Now, if you get two elements, then you get the whole set. So that's already set A. On the other hand, if you don't get any element, you get the empty set. So those are the subsets of A, and those are as well the elements of the power set of A. So all in all, we have four subsets: the empty set, the set itself, and the set containing singletons A and B. So let's try another one. What if the set contains three elements? So again, following the same technique, all we need to do is to identify the elements, to get the elements of A one by one, and then form a set containing these elements. If we don't get any element, you get the empty set. So we get the subsets of A as follow. So the empty set contains no element of A. If we get the sets containing just one element of A, so we get the singleton A, the singleton B, and the singleton C. Next is get any two of the elements. So by property of counting, so just get any two at a time. So A and B, or A and C, or B and C. So given three elements, taking two at a time. So if you remember the formula of n taken R, we have n elements taking R at a time. So that's n factorial over n minus R factorial. R factorial will be the formula So, 3 taken 2 is 3 factorial divided by 2 factorial times 1 factorial, or that's 3. So, we know that from that formula, we have 3 elements of the power set with 2 elements of A. Now, if we get 3 elements of A, then we get the whole set, A, B, C. So, all in all, we have 1 empty set, 3 singleton, 3 containing 2 elements, and 1 containing all. So, we have total of 8 subsets of A, which comprises of the power sets of A. So, we simply write this as a set. So, the power set of A is simply the set containing the empty set, the singletons, A, B, and C, the 2-element subset, AB, AC, and BC, and the set itself. So, those are the elements of the power set. And finally, if we have 2 sets and we want to say that these sets are equal, then that means, by definition, every element of A is an element of B, and every element of B is an element of A. Okay. So, how do we show that 2 sets are equal? We usually use the definition as follow. Because every element of A must be an element of B, so that means A is a subset of B. But it also means that every element of B is an element of A, so B as well is a subset of A. To put it simply, and we call that a two-way inclusion, 2 sets A and B are equal if and only if A is a subset of B and B is a subset of A. So, we can write that as follow. So, A is equal to B if and only if A is a subset of B and B is a subset of A. So, that means, again, that's two-way inclusion. You need to prove 2 things. If X is in A, then that should mean that X is in B. And at the same time, you also need to prove that if an element X is in B, then that element must also be in A. Well, that's actually easy to prove, since by definition, A is equal to B if and only if for every X is in A, if and only if X is in B. But in logic, that means that X is in A and X is in B. Rather, if X is in A, then X is in B. And if X is in B, then X must be in A. So, this means that X is a A is a subset of B and B is a subset of A. So, this is a very good technique whenever you want a set, 2 sets to be equal. All you need to do is to show that the first set is a subset of the second set, and the second set is a subset of the first set as well. For example, let A denote the set of positive even integers, and let E prime denote the set of positive integers which can be expressed as sum of 2 positive odd integers. So, we want to show that this set are the same. Again, let's write E in set builder notation. So, E denote the set of positive integers. So, how do we write the set of positive integers? So, we want the positive even integers. So, as we've done a while ago, so we have 2n such that this time we only want n to be the set of natural numbers. So, we don't want the negative even integers. So, E can be written as the set containing 2n for all n of the set of natural numbers. Now, how about E prime? E prime is the set of positive integers. So, if you write E prime, so you have, it contains the positive integer. So, it contains the set of natural numbers such that any element here can be expressed as sum of two positive odd. So, to write that, we have n can be written as p plus q such that pq are odd, positive odd. Positive odd integers. So, that's our representation for E prime. So, now what we want is to show that E and E prime are actually the same set. For instance, if you have 2n, let's say 6, we know that 6 can be written as 1 and 5. So, 1 plus 5 are sum of two odd integers. So, if we have 6 to be an element of E, we know that 6 can be written as 1 plus 5, which is an element of E prime. So, we have an example here where an element in E is also an element of E prime. Now, of course, this is not yet the proof. We are just establishing the property of E and E prime. Now, on the other hand, if I get an element of E prime, is it an element of E? For example, I get two odd integers. Let's say I get 3 plus 7. Now, 3 plus 7 is 10. So, indeed, 3 plus 7 is an element of E. So, we started with an element of E prime and we end up with an element of E. A while ago, we started with an element of E, then we were able to show that it is an element of E prime. So, that's what we want to show. We want to show in general that it is true. So, how do we do that? So, again, we will make use of the two-way inclusion. First, we will show that the first set is an element of the second set. So, we want to show that E is a subset of E prime. So, how do we do that? So, let X be an element of E prime. So, what do we mean by an object to be an element of E prime? So, this would imply that X can be written as 2n for some n in the set of natural number, because that's how we define an even integer. Now, looking at our technique a while ago, we can easily find two odd integers. For instance, 6, that's simply 1 plus 5. So, that means all we need to do is to get this value added by 1. But this value actually is 6 minus 1, right? So, 6 can be written actually as 6 minus 1 plus 1. 6 is our value 2n. So, that means this can be written as 2n minus 1 plus 1 for some n of the set of natural numbers. But now, 2n is an odd number, which is positive, right? And 1 is also an odd number, which is also positive. So that means we were able to express the number x as sum. So x is a sum of two positive odd numbers or integers. And this is the definition of the elements of E prime. So that means, so this would imply that x is in E prime. So we started with x being an element of E, and then we end up x being an element of E prime. Therefore, we conclude that E is a subset of E prime. Now, for the next inclusion, the other way around, we want to show that E prime is a subset of E. So we start with the fact for E prime. So let x be in E prime. Again, what do we mean by x being in E prime? We can express this as sum of two odd integers. So it would necessarily mean that x is equal to p plus q for some positive odd pq. But what is the formula for odd integers? So the formula for odd integers is simply 2 times n minus 1, right? So we can write p as 2n minus 1. And we can write q as 2, let's use another variable. Let's say 2m minus 1. So here m and n are natural numbers. Right? So meaning we can find natural numbers m and n such that we can write p and q as 2n minus 1 and 2m minus 1. For example, if we have the odd number 13, 13 is 2 times 7 minus 1. Alright. But we can rewrite this as, right, we can write it as 2n minus 2m minus 1, or that's 2 times n plus m minus 1. Now, of course, n and m are integers, so n plus m minus 1 is a natural number as well. So 2 times a natural number makes x an even number. So x is an element of E. We started from the expression x is in E prime and end up with the expression x is in E. Therefore, we conclude that E prime is a subset of E. So, by two-way inclusion, that means we have the desired equality. So that wraps up our discussion about set and subset. A few notes to remember. So you have a set to be collection of distinguishable objects. Now you have two methods to write a set. Either you list the element, so that's the rule method or the roster method, or you describe the element. For the rule method. Usually, when we describe an element, we write the properties as follow. X is an element of a set A such that the property P of X holds for this element X in A. An element or a set A is a subset of B if and only if you follow the definition for any object X. If X is in A, then X must be in B. An empty set is a set containing no element or any object that contradicts each other. And finally, the power set is the set of subsets, or rather let's call it collection of subsets.